Good afternoon. I'm Ruggero Donidolabati. I'm the chair of the B4SEC Technical Activity Committee of EURASIP, and I'm glad to introduce you Simona, Dr. Simona Samardjiska, who will give us today a webinar entitled Algebraic Methods in Code-Based Cryptography. Dr. Simona Samardjiska is an assistant professor in post-quantum cryptography at the Digital Security Group. Her expertise and research interests are in the mathematics of post-quantum cryptography, multivariate and code-based cryptography. She has been actively involved in the current NIST post-quantum standardization process as a principal submitter of the second round candidate MQDSS and one of the submitters of MEDS in the new fourth NIST signature round. Besides being a designer, she has also contributed to the understanding of the security of several finalists and second round candidates by analyzing their classical security and resistance to side channel attacks. She has published on several IACR conferences, journals, and IEEE symposiums, and has been program committee member of various cryptography-related conferences and workshops. She is an editor of the EURASIP Journal of Information Security. She is an activist of gender balance and diversity in computer science. Simona, please. The floor is yours.
Thank you very much, Ruggero. And thank you for having me at this webinar and allowing me to share my research with you. So today I decided to talk to you about algebraic methods in code-based crypto. So this is maybe the best intersection of my interests in post-quantum cryptography because from one point of view, I'm interested in how to apply algebraic methods. And I think maybe for the community of EURASIP, codes and coding theory are the closest probably to what I do. So I made this nice overview of these methods in code-based crypto. So if you're maybe not familiar with what this means, I will, of course, explain what we mean by algebraic methods. So, let's see. Let's see. Okay, yes. So, algebraic models, what's that? Okay, so first, imagine you have a crypto system, whatever crypto system you can think of. For example, that can be an encryption scheme or digital signature, whatever, a CAM. So let's say this is some sort of a crypto system. So we judge the security of the crypto system in many different ways. But one of the ways is by doing cryptanalysis on it. And algebraic models give us a one way of looking at this. So we take a crypto system and then we think of some specific model, which is this part here, of how to transfer the essence of the crypto system into a system of equations. So what do I mean, a system of equations? Well, often the crypto system would be defined over some, let's say, a finite field. It doesn't have to be a finite field, but let's say. And then we try to make the model over this finite field or a related finite field. And if you take a look at this system here, even though this is just some like a very small, tiny example, you will see here that we can have nonlinear terms. There are some linear terms, but the point is that there are some nonlinear terms. If this would be a linear system, then that's easy to solve. However, once we have a nonlinear system, that all of a sudden becomes very, very hard. Actually, this is one of the hardest problems that we know of, and it is NP hard or NP complete, the decisional version of it. So now, looking at the system, we would like to solve it somehow. The solution that we get in the end, for example, one that we see here, can be somehow in a meaningful way be used back in the crypto system to break its security. So think of a message recovery attack or signature forgery or whatever. So it can be on different levels depending on what we were able to model algebraically. How we solve the system often includes non-trivial methods. The non-triviality here comes from two perspectives. First, it is difficult to solve these systems. Well, sometimes these systems are easy to solve, but then we break the system. But figuring out how to solve them is also not that easy. And then figuring out the complexity estimate, unless it is something super efficient when nobody would care what the complexity is, because we see that it's super easy. Figuring out these complexity estimates is also a difficult problem. So we have several challenges: the modeling and then the solving, and some problems there. Okay, so let's first see how we solve algebraic systems and what do we mean by that. So the simplest method is that of linearization. I mentioned that if this were a linear system, then it would be easy to solve. Okay, so why don't we try to turn this into a linear system? So what we see here, for example, is a system that has n variables and m equations. And then we can take each of these monomials here and replace them by a new variable. So make some change of variables. And what we get in the end, this thing here, this is a linear system. However, because, for example, this was a quadratic system and we changed every monomial with a new variable, this means that we have, on average, n choose 2 variables. But we have m equations. So whether we will be able to solve this system really depends on the equations. When I mean solve, I mean find easily a solution, because you would say, like, okay, even if this were a non-indeterminate system, we can solve it, for example, using a Gaussian elimination. But then we would have a huge space of solutions, and not all of those will be solutions to the initial problem. So that's why we would like to have enough equations. So the number, of course, this would require that we have quite a lot of equations, and we would like to have a unique or almost unique solution. And then this means that this m needs to be at least bigger or equal to n choose 2. Okay, so second. Yes. So once we have this, we can estimate the complexity, and the time complexity is, of course, the time complexity needed to solve this system. Here, the space complexity, of course, is the space needed to put in the corresponding matrix in memory. So it's easy to estimate this. But what if we do not have these m bigger than n choose 2? Can we solve the system? The thing is that the initial system, if we have approximately the same amount of variables and equations, the initial system will also have approximately always a unique solution, whereas we have turned it into something that blows up the space of solution, but not of the second system. They are not solutions, all of them solutions to the first system. So what can we do? What can we do here? We have some general principle solvers like F4, XL, JUVITS, and these are somewhat different algorithms, but in essence they are the same. The underlying ideas are the same. And so in order to explain to you how do these algorithms work, let me just quickly make like a general framework for this. So imagine that this system that is given here has a unique solution, this one, U1 to up to UN. And we can, for example, write this as x1 minus U1 equals 0. But this means that if this is a unique solution to this system, these polynomials P1 to Pm must generate the same ideal generated by these here. So you can think of this as a super nice basis of this ideal, because it's given just by some linear terms. This will often be the nice basis that is known as the Grobner basis, but yeah, but that's well, let's say Grobner basis can have different shapes depending on many things, but we will not go into that. The point here is to notice that, well, if both of these bases, the one given by the initial polynomials and the one given by the nice basis including the solutions, this means that using these bases, we can write these tiny linear polynomials as linear combinations of the initial systems, which is this thing here. So now the goal is to find these linear combinations. So we now know that there must be such linear combinations, but we don't know how to find them. So the problem is that these HIs, these are combinations in the ideal, and these are polynomials. So they can be of, we don't know of what degree, shape, and so on. And it is just like enumerating, this would be huge and impossible to find. So it's not, this is not an easy task, of course. And another problem is that because these are polynomials, manipulating them in an algorithm turns out to be notoriously difficult for practical reasons. And then we try to make something that is much easier to work with, for which we have potentially also faster methods. So we form a huge matrix, but this matrix does not live in the ideal anymore, but it lives in the field over which these polynomials were defined. But we try to sort of simulate what would happen in the ideal. So we form this matrix where the columns are indexed by the monomials, and where the rows are indexed by the polynomials, and polynomials multiplied by all possible monomials up to the same degree. So we have the same degree polynomials in the rows and in the columns. So why is this nice? So by doing some Gaussian elimination on this matrix, we can actually reach or find these unknown elements or unknown HIs that we require to find the nice basis and also our solutions. So when can we actually find a unique solution? Well, if this matrix is of sort of a full rank, and we have enough in the sense of the columns, so full column rank, and then we need enough independent rows to Gaussian reduce this. And this, when we get these independent rows, this tells us which degree D we need to go to. And again, because this is Gaussian elimination, we can easily tell what the complexity in the end is. Okay, so there are several issues here. First of all, rows can have dependencies, which we call syzygies. And for example, this one is always there. It's by design there because of commutativity over the polynomial ring. So this has to be there. But these are called trivial syzygies. And sometimes we have syzygies that are not trivial and that depend on the structure. Even though we can notice structure in these polynomial systems, it is often extremely difficult to express this structure in terms of syzygies. So this is one of the interesting or always challenging questions in this part. Okay, So min rank, what is min rank? So this is basically the favorite algebraic exploit that we try to use everywhere. And I will give you some examples of this one. So what is a min rank? So it's a very simple problem that is known to be NP-hard. And given a set of matrices, these here, and a target rank, we want to find some linear combination of these matrices such that the rank is R. So the linear combination of the matrices is another matrix that has a particularly, let's say, different rank from what we would expect. And this is often what we see in cryptography. So for example, if we just have a set of random matrices, we will certainly not expect to see a rank 2, for example, in the space of these matrices, because this is not expected in this space if this were random. So we would at most expect n-2 in these matrices. But then if this were, let's say, if this is made as part of a crypto system, sometimes we can notice that there is something that is of very small rank, for example. So one important way to model this problem is known as the Kipnis-Shamir modeling, where we take this matrix that we are looking for, the blue one, and we know that it has at most rank R. This means that it has at least n-R kernel size. So then we have n-R unknown kernel vectors, and we also don't know. So we don't know these coefficients, and we don't know these elements, these coefficients here in the basis of the kernel, because we can always assume, for independence, we can always assume that this is the shape of the basis of the kernel. And then we can model this algebraically, and this is done often in cryptography. So it's very easy to model this algebraically. It's a set of bilinear equations. So we have the red ones from the left part, or from the kernel, and the blue ones from the matrix. And then we can estimate the complexity, and this is a very complicated formula, but if you see this, if you see the shape, it is something choose something to the power of 3, which means that we are solving it algebraically using the previous idea that I showed you. And we are here, we see that in the choose part, we have that this would be +1 of either the blue set or the red set. And here we did not use a specific structure that comes from these being a sort of a matrix product. And I will show you, right now, that actually, if we take this into account, we can reduce this complexity further. So this is these are some references that if you're interested, you can look up and see how this was done, but it's quite more involved that we're interested at this point. Okay, so I mentioned that I will show you some nice examples, and these were this is a crash course of the most most often used methods in these algebraic attacks. And so I will show you 3 examples of nice algebraic models. The first one is the standard syndrome decoding one that many people have worked on, and the second and the third are examples that I've worked on, but that are particularly interesting because they are in a different type of setting. So syndrome decoding, you probably all know what syndrome decoding means, but we will see that soon. But the scenarios for which syndrome decoding can be modeled algebraically and solved are for high rate codes when we have some sort of regularity in the errors. For example, we know that in each 3 positions we have one error when we know, for example, the channel sort of presents some specifics in how the errors occur. And then we have different types of metrics. So for some metrics, it's very, very easy to model the syndrome decoding algebraically. And what I've been working on is on using this in the context of decryption error and also in code equivalence. Okay, so let's dive into these. So coding theory basics, I suppose I don't need to tell you coding theory basics, but maybe it is useful from the point of view of how this is used in cryptography. So for example, in crypto, we like to use the Hamming metric, and we also like to use the rank metric, where the Hamming metric tells us the non-zero coordinates in a vector, while the rank metric gives us the rank of the matrix representation of some code word. Or it can be simply the code word can be a matrix. And then we have isometries. What are these isometries? Well, they preserve distance, sort of. So if we have in the Hamming metric, if we have a code word and we transform it somehow, we want in the end to end up with another vector that has the same Hamming weight. And this would be some sort of scaled permutation matrices. So any permutation on the coordinates, even if you scale it, will preserve the Hamming metric. Whereas for the rank metric, this can be any multiplication by any two non-singular matrices A and B. So these are isometries. And what is syndrome decoding? Well, given a parity check matrix H and a syndrome S, find a small weight error such that H times E equals S. If we did not have the restriction that this E has to be of small weight, then this is easy. It is easy to find this just by solving this equation and just by finding any solution in the solution space. But the point is to find a small weight error, and this all of a sudden becomes an NP hard problem. And then we have another interesting hard problem, and that's code equivalence. So given two codes, well, they have the same parameters. We would have to have the same parameters, otherwise this problem is not difficult. But if they're, for example, defined over the same field, they have the same dimension, the same length, then the goal is to find an isometry, if it exists, of course, such that one code is mapped to the other. And so this is also a hard problem. It is known not to be NP hard, but it is still still hard. So, and these problems occur constantly in cryptography. So what are rank codes? Well, it can be a matrix code where the code words are simply matrices and doesn't have a lot of structure, but it does take a lot of space because we need to sort of store the matrices. But we could represent these matrices over the extension field as vectors, and then we still have the rank metric, but we do represent these as vector codes. The problem here is that this has become an FQM linear code, and this introduces some structure. But first, let's see what do we mean by this taking less space. For example, if we look at code words, like let's say this XG is a code word in this space, or for this code, we can represent it as a linear combination of the rows and over FQ to the M. And if we represent the coefficients of this linear combination over the ground field for some basis B1 up to Bm, we get the next sum and so on. And so if we look at the last sum, so these are some, we can look at these as some basis matrices over FQ if we represent this these GEIs also over FQ. And well, we need for the storage of this thing, we need this much space. Whereas if we just do everything over FQ to the M, we need a factor of M less. And further, there is another benefit that we have efficient decoders for these codes. So we can potentially use these efficient decoders for in the honest setting of the crypto systems, not from the attacker point of view. But this also means that potentially this can be exploited. So what is the rank syndrome decoding? Well, it's again the syndrome decoding, but over the rank metric. So given a syndrome, find an error such that h times c equals s, and e is of small weight. In this case, this is the rank, so it's of small rank. Already almost 20 years ago, this was looked at and from an algebraic point of view by Lévy, Diderot, and Perret. And it was modeled in a very natural way as follows. So if we, what does this mean that we need this error to be of small weight? Well, if we represent the syndrome equation, this equation here, if we represent it in this form here, this can be further represented like this. So this C minus mg needs to be of small rank. And if we do the same trick of transforming this over the ground field, we end up with this expression here, which, if we represent it over the ground field, this is a linear combination of matrices that we don't know. So we were looking for this m, and this m turned into these unknown coefficients in front of this matrix here. So this is something that I showed you before, and this is called min rank. This is min rank, and but min rank with these specific parameters. And we can model it using Kipnis-Shamir, and we get some number of equations and some number of variables. And once we know this, and once we know that this is in the Kipnis-Shamir model, we can use the best possible estimation methods that we've had in order to tell how much time do we need to solve it. But like if we compare Kipnis-Shamir models, it is very easy just by looking at the number of equations and variables to tell which one will be better or which one will be more efficient. Okay, so we could also improve this slightly if we directly look at the syndrome decoding equation. So, for example, if you look at the error can be represented using the support of the error and some unknown basis E. And then if we further represent the support of E as a base, using the basis of fq to the m in the ground field as a vector space, then we get this equation here. So we also don't know the f, and we also the big F, the capital F and the capital E. And if you see, we would have again a matrix multiplied by matrix where we don't know the variables in one or the other, which means that again we have a very, very similar system to the previous one, the Kipnis-Shamir model. That is a system of bilinear equations. So we have approximately the same amount of equations, but for the right parameters that this is being used in cryptography, we have a square root of n less variables, and this immediately brings some advantage. And if we think of several different bases of E, we can further fix some more variables. We can reduce by a small constant as well here. Then in 2002, that's a long time ago already, Orowski and Johansson figured out how to use this FQM linearity. This was not used previously. If you followed the reasoning, I told you I never mentioned that these are FQM linear. But this indeed helps in solving this, and we can use a common idea from coding theory, and this is about to augment the code using this C. So if this is the equation, and this is the E that we want, if we augment this C with this C, this means that in this augmented code we will also we will also have linear combinations over the extension field that will also be solutions to our system, which means that we all of a sudden this equation over, like we can then use the same thing as previously, using that over the augmented code, all of a sudden gives us larger solution space, and all of them will work. All of them will be lambda E, and all of them can be used to extract the E in the end, but we will have more freedom to fix more variables and reduce further the complexity. Okay, so that was the standard algebraic approach used in code-based cryptography, but we then, like some years ago, we then started to use algebraic methods on other problems, and for example on LRCP, LRPC codes, which are something like LRPC codes, which are over the Hamming metric, but these are over the rank metric, and it's approximately the same. So the idea is that the parity check matrix lives in a very small FQ subspace of FQ to the M. And how do we use this in cryptography? Well, we start with linear codes that have this sparse H, and we mask it using some nice structure. And some more details. Well, we can represent each of these coefficients using the basis of this small space that we call F here. So let's say this lives in a very small space of dimension D, and this D can be very, very small, like 3 or something, right? And then these are nicely decodable, but once we mask them to hide the structure, we destroy all of these. We get out of this subspace, and then we cannot use this anymore. So think of this as a public key of this LRPC crypto system. So quite a lot have been proposed, and many of these are actually the three, except the first one, which is a long time ago. The 3 other were submitted to NIST for standardization. And how do we came up some years ago, we came up with a way to exploit decryption errors. And decryption errors are errors that in code-based cryptography are errors that occur because of decoding failures. So simply the decoder cannot decode the error, and then this causes problems in decrypting in the crypto system, and therefore an decryption error. So let's see how this can be used by a malicious attacker. So imagine this some protocol between the attacker and the nice guy, and the attacker just tries out a lot of let's say code words C1 to see when the nice guy will potentially fail. So for example, let's say C1, decode this, doesn't work, and so on and so on. And at some point, the attacker created some, in this case a triple, created some triple that the decoder cannot handle. So yeah, there are many types of codes for which there is a small chance of decoding failure. And for example, he realizes that, well, for this CT, decoding fails. And then the nice guy says, like, oh, something went wrong. I could not decode this. Can you please resend? And actually, this nice guy doesn't say anything except that there was a failure. And this is all that the attacker actually needs to figure out a way to attack the crypto system and potentially break it and obtain the key. So as little as that. So this is very interesting, because at the beginning of the NIST competition, people were not aware that decryption errors can be so powerful. So they had decoders that could fail with an error of, let's say, 1/2⁵, which seems very, very little if you think about it. But then it turned out this can be exploited to break the systems, which is, I find it sort of fascinating. So we discovered that for our PC codes, this happens if the syndrome space has rank defect. And this is what I mentioned previously about min rank, and this is our favorite exploit. So how did we do this? So let's look at a syndrome equation for an LRPC code. So a lot of symbols here, but the essence is to look at these spaces F and E that we had. So we know that this code lives in a small subspace of dimension D, and the error lives in a small subspace of dimension R. And this is the equation that we get in the end. But in matrix, if we write this in matrix form, the basis that we have on this side here, well, this is certainly a full rank because these were the basis of the two fields. And what about this A here? So we know that in these cases, I will not go into details, but decoding fails if the dimension of the syndrome is smaller than this RD. And what can be the dimension of the whole thing smaller than RD? Well, if the left-hand side, if the left side or the circle one now that you see is always a full rank, this must be as a result of a rank defect in this matrix A. And this is what we exploited to mount an attack. Okay, sorry. So this is basically the attack, but the point is that first we collect a lot of messages, errors, and ciphertext, and we form this system of equations here. And once we and then we exploit this rank defect. And once we have found the coefficients, we can also find the basis of these F and E spaces. Sorry, yes, the F space was of the parity check matrix, and it's easy also to find the E spaces. And then we're done. So this means that we have we need to collect some messages, errors, and ciphertext. Well, if the probability of failure is 1/2⁵, for cryptographic purposes, it is indeed possible in 1/2⁴ or something like that to find enough errors so that this can be exploited further. Okay, so this is again min rank instance. So now I will move to a matrix code equivalence problem. So maybe this will, should I stop, or do I have some more minutes to briefly explain this?
Please continue.
Yes, okay, great. So the matrix code equivalence problem is what I told you previously, where we want to find two, we want to find the isometry between one and another code that we know that they are equivalent. And we did some work on this to figure out how difficult this problem is, and we could put it into some framework or into a class of a complexity class where we know, for example, what is the asymptotic complexity. But what is interesting is what is the practical complexity. So one way is to model this algebraic. And so the easiest way is to take two bases of the code, so C's and D's, these are the bases. And now we can write this as a system of equations where we want to find these matrices A, B, and T that give us the isometry. And it's easy to write this as a system of equations, something like this. And the unknowns are the black, the red, and the blue ones, and these are the unknowns. And if we look at this, so we have the A's and the B's somehow. So we have, for example, these rows here will only multiply the columns, and from here we can build a bilinear system where we can, for example, choose a bunch of rows in A and only focus on this one. So for example, for m equal n and equal k, the number of rows can be only 3. And then we can form the system, and this is a bilinear system. As I told you before, we know how to solve bilinear systems, so this will be the complexity. So still, this is a huge number here. It's yes, it's exponentially in n. So this is not this is a straightforward way of how to model this, but we can of course try to do better. So remember that we had this t here, and this t simply gives us the transformation from one basis to the other, but these bases are not given. So what if we don't include this? So we know that this thing here should be the code, right? So we start from C, and this is the other code. So this t really doesn't matter for the isometry. And we can use tricks from coding theory, and that's the relation between the code and the dual. So we can, for example, like take these matrices, the matrices, and sort of stretch it to obtain these representations. This is just for convenience, but you can also directly start from the matrices to form these. And we know that the code and its dual are orthogonal, right? So if we take the dual of C that we know, this should be orthogonal to the unknown transformed sort of basis of this one. And this is of course the code D, but now it is represented in terms of the unknowns A's and B's. And what we see here, so this part here will be our new algebraic model. And then we get much better estimates than the previous one, much better ideas. And we can go one step further, and this is called the tensor view. Well, what does this mean? Well, these are matrix codes, and we can put the matrices like in a sort of a row to form some sort of a cube. It doesn't have to be of the same dimension, right? But the cube can be seen from a different side. This should not matter for the structure of the code, or like this. So this means that we can look at the codes from these 3 perspectives and form 3 different systems of equations. And these are the systems of equations that we form for the A and B unknown here, for the B and T, and for the A and T. And now you will say, okay, well, didn't we try to remove this T in the previous slide? Okay, and this is the equations that we get. And then why are we introducing these T's again if we remove them? Well, it turns out that sometimes you can do that and make some sort of a trade-off. So we introduce slightly more variables, but we introduced many more equations. And the more equations you have that are meaningful, the easier it is to solve the system. So then we have this system to solve, and this is the number of equations, this is the number of variables, and then we can make some estimates. And so now the tricky part is how to estimate this. Well, it turns out that the system that we get is not semi-regular, which means that there are syzygies that are not trivial. So this means that not all rows in our system, if you remember at the beginning of the talk, not all rows are independent apart from the trivial ones. So there are many more dependencies. So we need many more rows than we would in the regular system, but it is still better than the previous idea. Okay, so the story doesn't end, and soon we will have even a better modeling, which will appear at AsiaCrypt, which you can, of course, see later on, so later in this year. So we even more improved this, but I will not talk about that. What I want to say in the end is that sometimes we can combine the algebraic attacks with some combinatorial tricks, and this is the Leon. Okay, the Leon as algorithm in the Hamming matrix. So I will not talk about it. But the point is that here we, due to time constraints, I don't want to keep you there. But the idea in the Leon's algorithm is to combine both combinatorial ideas and algebraic ideas. Although, in light of our new result, it turns out that still what I showed you here and the pure algebraic attack works better. So the pure algebraic modeling works better because combinatorial approaches often require enumeration, and enumerating over a finite field can be tricky, especially if the field is large. And then taking a larger field for a crypto system makes these combinatorial attacks very inefficient. But this doesn't mean that the system doesn't have any algebraic structure that can be exploited algebraically. So that's why we are interested in this, where increasing the field size really doesn't matter. So this would be the summary. So there are some open problems that we want to tackle as well. Algebraic attacks have gotten a bit of sort of a boost in the last few years, even though they're very old and very well, let's say, very used in cryptography. But nowadays there's a sort of like a second generation of algebraic attacks where the smarter techniques are being introduced, and it is interesting to take a look at some long holding problems that were not solved algebraically previously, like, for example, LWE or lattice isomorphisms. So thank you very much for listening. That's all, and I can take some questions now.
Simona, thank you very much for your presentation. Any questions? Well, maybe yes. I see a raised hand, but I cannot. Okay. Any question? Okay. Maybe we are waiting for some questions. So I'd like to ask you, Simona, since you gave a very nice presentation about these problematics and these methods, but since most of the participants, I think, are young researchers, what are the open research fields? What are the open questions in your research which could be interesting for them? For example, maybe they want to work in this field and they want to just start.
Yes. So indeed, this was a sort of like a talk to put into perspective of how to use these algebraic models in, let's say, in attacks, and especially in coding theory. And coding theory should be something that is, I suppose, very dear to this community in general.
For sure.
So it turns out that often you can use some known results in coding theory that you can apply here, like the one that I showed you in the end. So matrix code equivalence, even though it's over codes and so on, in the essence of how it is used in cryptography, you don't use decoding at all. You just use it. You can just take random codes. We don't know how to decode random codes. You can take random codes and use them in a crypto system. So at no point you will you need to decode these codes, but you still can use tricks from coding theory to try to model this properly. So yes, I think that it is very interesting to use more knowledge from these fields. So also in the previous attacks, so we extensively use knowledge from coding theory in these attacks. And while this is clear in code-based cryptography, in many other areas of cryptography, people are not so familiar with coding theory. And I think one of the ways of really joining these communities is to really use the knowledge that you have in coding theory to attack these attacks. And what you see here in the summary are indeed some questions that can be looked at, and I think many of these are of how to model algebraically the properties of codes. So, for example, a classical example in cryptography is the use of GOPA codes. So these are algebraic codes that, even though that they've been there for 40 years and used in cryptography, using this algebraic structure was sort of elusive, and people still don't know how to use this, let's say, in order to cryptanalyze this problem. There is some let's say some movement in this direction in the past 2 years, I would say, but it's still at the beginning. But I would definitely look at these problems here. So if you know, or if the participants are maybe aware that LWE is the problem that underlies the new crypto systems in post-quantum cryptography that are standardized by NIST. And it's basically decoding, but in the Euclidean metric. So this is very interesting, and maybe using coding theory ideas for breaking LWE is something that I think young researchers can contribute a lot.
Okay, thank you. You gave many ideas for young researchers, definitely. Any questions? You can write your questions in the chat. You can raise your hand. Okay, I don't see any other questions, so I'd like to thank you. Thank you to Dr. Simona Samardjiska for the beautiful presentation, and thank you everybody for attending this webinar.
Thank you again, Ruggero, and thanks everybody for being here.
Thank you. Goodbye.
Bye.